Thank you for coming to UTIG seminar. And this morning we have Shuo Zhang, who is a postdoctoral fellow and joined UTIG only like a couple of months ago. And he didn't travel very far. He just moved here from Dallas. And there he finished his PhD in seismology with one of our former colleagues, Hejun Zhou, who used to be a distinguished, JSG distinguished postdoctoral fellow here a few years ago. And before joining UT Dallas, Shuo Zhang actually did his undergraduate degree at China University of Petroleum. And actually, I met him very briefly when he was an undergrad, but I didn't know he was the same guy when he applied. But so he comes highly recommended by Hejun Yu. So he's worked on full waveform inversion for global structure, global scale structure, and also crustal structure. He will talk about that in his talk based on his PhD work. And the main reason I got interested in having him here was that, we worked on some hybrid full waveform inversion methods, but we have not applied to any global seismic data set for whole earth structures. I thought she'll be a good candidate to do some research on that. At the same time, we're also looking at seismic full waveform inversion in anisotropic media. So these are the two projects that we have for him, but of course, he's free to pursue some of his own interests. So let's welcome Shu, and pleased to have you here. Thank you.
Oh, yeah, okay. Can you hear me? Okay, great. So thanks for getting this opportunity to present in front of the colleagues. Sorry, in UTIG. So this presentation is based on mainly based on my PhD thesis, and the topic is the spatial and temporal variations of seismic velocity within the crust of Oklahoma. So this. So for this presentation, I mainly will first give the introduction and motivation of my project, and then we use the waveform inversion to construct the 3D velocity model for the crust of Oklahoma. We also trying to tracking this temporal and spatial variations of this near surface seismic by using the ambient noise, then with some summary and the future works. So first, the brief study, the seismic velocity has been widely used to study the internal structures of the Earth. Like it can going from this exploration scales and to some regional subductions of magnetic flows, or even people are trying to build the 3D velocity model for the whole Earth. It can give us a lot of geological structures on the informations of the deeper Earth structures. And later, people also find that these velocity variations can also help us tracking the dynamic structures of the internal of the Earth. Like in industry, people are trying to use this difference between the two seismic surveys to tracking the water migrations, subsurface water migrations from these injection operations. And later, when people come to compute the temporal variations of the seismic velocity, they find this coherence between this precipitation and these velocity variations. Like whenever there is a large amount of precipitations, they are always accompanied with a sudden drop of the velocity. And one of the famous application of this spatial variations temporal variations of the seismic velocity is this. They are using this velocity variation to track the occurrence of the earthquake. Like for this Parkville earthquake, there we can see the significant velocity reduction when this main shock of this Parkville earthquake occurred, and also which follows by this post-seismic helix. So and then in this project, in first step, we know that in Oklahoma, it suffers from the increased number of the induced earthquakes in last decades. as shown by this red line, it may start from 2013 and then get a peak at 2016 and then gradually recover to a normal level. And when you compare with this red line with this the injection volume, total injection volume shown by this black line, people always many people think that these induced earthquakes are triggered by these industrial operations like water injection and or solid water disposal. But most current earthquake catalogs are based on the 1D velocity model, and there are several studies showing that this the accuracy of the velocity structures has a great impact on these earthquake source parameters. Like it can this comparison between the 1D and 3D velocity model can significantly impact these earthquake locations, and also it will increase this uncertainty of the momentous solution of these earthquakes. Therefore, but in Oklahoma, in current stage, we don't have a widely used 3D velocity structures. Therefore, our goal in these steps is to use the waveform inversion to construct a 3D velocity model for crust of the Oklahoma. So here to improve the to constrain the resolution and the accuracy, we in our workflow we actually involve two mixed functions. So one is based on this phase difference, phase difference, and then we switch to this waveform difference to improve the accuracy of the inverted model. And since in these steps we do not take care too much about the amplitude of the seismic recordings, therefore this density is updated by this empirical relationship. And since when we're checking our the data collections, we have the three components data, the transverse, radial, and the verticals. And when we check those observations, we do find this really large discrepancies. Therefore, in our final velocity models, we have four terms: this vertical and horizontal components of the P wave and the vertical and horizontal polarized shell waves. And taking advantage of these induced earthquakes and the widely deployed stations in Oklahoma, we actually use the 226 earthquakes and 52 stations for our immersion. So we can see these earthquakes are widely ranging from 2011 to 2017, and many of them are shallow earthquakes surrounding around 5 kilometers. And you can see the magnitude is pretty somehow small. It's ranging from 3.5 to 4.5, most of them. And as we know, this initial velocity model is an important input for the successful waveform inversion. So here we use this initial velocity model borrowed from previous study, which is established by the combination of the waveform inversion and the ambient noise cross-correlation functions. So from these figures, we can see the initial velocity model can already see certain features, but with a very low frequency, very low accuracies and resolutions. And therefore, we are trying to improve it. So we actually applied 18 iterations, and after finally we get this data misfit reduced by about 40%, as shown by these figures. We to mitigate this well-known cycloscaping issue in waveform inversion, we actually apply this multi-scale strategy, set 3 frequency band from 10 to 30, 5 to 30, and 2 to 30. So for all three data component, we can see the data misfit reductions. And for the last 5 iterations, we apply, as mentioned, we also apply this waveform difference to further improve the accuracy and the resolution of the inversion result, as shown by these final parts. So if and shown by these histograms, we can see comparison when comparing with the initial velocity model, the inverted velocity model can help us further improve this mean travel time difference between the observation and the predictions. So especially for this radial component, after the inversion from by this red line, it's more like a Gaussian shape and concentrated around 0 seconds. And then we we use the one earthquake as example to check what's the real performance of the inversion result in data domain. So here is the one earthquakes shown by this beach ball and the all corresponding stations. And this figure shows the vertical transverse and the radial and transverse component of the seismograms here, where this black lines are the observations and the red lines are the synthetic data. So in this figure, in this slide, this red lines are based on the initial model, and I filter it into 5 to 30 seconds. So we can see in the initial model, we do have the larger data misfits in this transverse component and in the radial component. And then if I, oh sorry, a mistake. Yeah, this slide is for the initial velocity model, and we can see. Oh, okay. So we can see the large. Yeah, we can see the large misfit. And then we turn to the inverted velocity model. Almost many of these misfits are removed. So these red line and black lines are fit with each other pretty well. If I flick back and forth, we can see the improvement in the phase. And also, if I enlarge this frequency band to involve more higher frequency components, we can see our inverted velocity model. There is another advantage of our inverted result is that we can not only fit those first arrivals, this P body waves and the fundamental Rayleigh waves, but also we can fit those higher order surface waves, later arrivals. And then we can go to the model domain to check the performance of the inversion. So we first compute this average depth profile of the inverted result shown by this two solid line for P and S waves, and then compare it with this 1D velocity profile used by Oklahoma Geological Survey, shown by this dashed line. So we can say, generally speaking, those two depth profiles are which are consistent with each other, although we have certain disagreement in the shallow part from 2 to 5 kilometers. And then if we also cut certain horizontal slides to show our inversion result, the inverted shell velocities, and also the radial entropies. So here, what should be mentioned is what should be mentioned is that in our inverted model, we have this 4 components, and for better visualization, we define this radial entropy parameters to which are plotted here. So this actually tells us the relation between the horizontal and the vertical component of the velocity. So check some details of the horizontal slides. So for this first row is the inverted velocity. So we can see most of this velocity anomalies, this fast and slow velocity anomalies, are consistent with those geological structures. Like we have this Cherokee and Daco Shelf and the Cherokee platform shown by this showing in this fast velocity anomalies, which might because of this limestone, the majority, the dominance of the limestone. And in contrast, we do see these slow velocity anomalies in these two Andaco and the Arkoma basin, which we believe is because of these sedimentary layers and also the sandstones, the slow sandstones. And if we go to deeper, we can also see certain some faster velocity anomalies, which might relative to this Arbuckle uplift and also South Oklahoma lockages. So so which means this velocity, this inverted velocity model can help us to better delineate the geological province within this Oklahoma. And also we turn to this radial entropies. We can see this radial entropy is comparatively simple than these velocity structures. It's the main feature of this radial entropy is that we have this positive radial entropy in the uppermost crust, while it's turned to the negative when we go to the deeper part. And we plan to explain it in next slides. So we also cut some horizontal, sorry, these vertical slides. I forgot to change the title. So we also cut some vertical slides to better show certain details in our inverted result. So we cut 3 lines. One is across this fast Cherokee platform, Cherokee platform, and another is go through these 2 sedimentary basins, and another is go across this Anadarko Basin and the Cherokee platform. So in this slide, I actually have 3 velocity model as a comparisons. So the first is the US 2016 velocity model. Is actually the 3D velocity model for the mainland of America. Therefore, when we concentrated in Oklahoma, it has really low resolutions and it loses a lot of details because it's inverted by the based on the receiver function and the fundamental Rayleigh waves. And also this second column are coming from the initial velocity model we used. So as mentioned, we can see certain structures like this fast velocity anomaly and the slow velocity anomaly in basin, but it's with a very low frequency and accuracies. Then the third columns are our inverted velocity models. So compared with the initial velocity model, we do see a lot of details in the crust, and also say if you go to this slow velocity Anadarko area, basin areas, you can see in our initial velocity model, it's the boundary is it has very low spatial resolutions. It has large smells beneath this slow velocity anomaly. But after the immersion, we remove this part, and also we from after immersion, we can better see this contrast between the between the velocity anomalies in Anadarko Basin and the platform. And also, as mentioned, in this radial entropy, we have this positive anomalies in uppermost crust, and which turn to this negative values when we go to a deeper part. And for current stage, we believe it's because of the different geological deformations. So this shallow, for this positive anomalies, it's mainly results by these sedimentary layer structures. Therefore, this horizontal component looks faster than the vertical components. And if for this Anadarko Basin, you can see this this Cherokee platform, you can see this same positive anomalies. Well, if you go to this Anadarko Basin, you can see this fast anomalies getting large in depth directions. And then if we go to the middle crust, when we meet this negative radial entropies, we believe it's because of the entropy of the minerals, like the mafic or mica or pelagious. So because of this east to west tectonic compressions, we have the vertical component is faster than the horizontal component. And that's all those explanations and trying to and analysis are trying to make sure that our inversion results is geologically meaningful. Then we go to what we are really interested in seeing to study this induced earthquakes. So we design a synthetic text to examine what's the impact of this velocity, the accuracy of the seismic velocity onto the earthquake locations. So here we put 140 earthquakes in this study region shown by this stars, and they use these blue triangles. Use this like a dense station network shown by these blue triangles to do the relocation. So here those virtual earthquakes, we put is widely distributed in the velocity in this study region, and also is distributed in depths from 5 kilometer depths, 10 kilometers, 15, 20. And then we compare the relocation results between based on the 1D and 3D velocity model shown by these two figures. So we can see from these figures, it shows horizontal the errors in the relocation in horizontal directions. So this blue red line is the relocation, the errors in relocation based on the 1D velocity model, and this blue stars shows the is the result from the 3D velocity model. So we can see this in the horizontal direction, those errors, those location errors are concentrated within 2 kilometers, and you can not, and it's pretty small. You can bear it can be almost ignored in real studies, and you can, from this figure, you can barely distinguish difference between the 3D and the 1D velocity model. But when you turn to the vertical depth directions, we can see the earthquakes well, based on the 1D velocity model, the errors can go up to about 10 kilometers. Well, if you use the 3D velocity model to do the relocation, it can reduce by it to about within 2.5 kilometers. And if you're considering that the maximum depth of this earthquake is about 20 kilometers, this 10 kilometers is a pretty large area. Sorry, error. Then we turn to certain real earthquake screens. In this stage, we only use taking this 2016 Fairwave earthquake as an example. So here is this location. This red dots are the location of these earthquake screens, and those are the black triangles at the station we use to do the relocation. So here after the relocation, we can see this. Those are the points of the relocations. We can from this anomaly animations. We can find out, we can see the geological structures in 3D domain of this fault line. And also, we have the collaboration with the University of Toronto. They used our 3D velocity model and the 1D velocity model to redetermine those the moment tensors of this mean shock of this earthquake screens. So here shows this beach balls. They get this 3D velocity model and based on 3D velocity model and based on 1D velocity model, and also they compare the result with the earthquake catalog from the St. Louis University. So we do see the significant difference between those among the three beach balls. And this 3D velocity model is more consistent with the fault plan we get from this. Sorry, from these relocations. And then we also trying to, so the second part of my thesis is trying to use tracing these spatial and temporal variations near the Earth surface for the near surface seismic velocity, and which the main purpose of doing so is to trying to monitor the groundwater, the water resources in Oklahoma. So, as affected by the global warming, this territorial water storage is widely used to describe all the water resources near the Earth's surface, which include this soil moisture, groundwaters, and the surface water, and also some rainfalls, snows. It's important can be almost directly affect the human activity and the productions. And among those, one important component is this groundwater storage, and people have studied and monitored those groundwater storage for a long time. And the classical way is to drill a well around certain aquifer and continually monitoring the groundwater depths. And also people can try to put certain GPS stations at the surface of the groundwater aquifers to indirectly monitor the groundwater storage based on these surface elevations. Those two methods can give us a very high temporal resolutions, but because of the deployment issue, it can hardly tell us how the groundwater aquifer migrate all the spatial patterns of this groundwater storage. Then people trying to use this satellite to measure this spatial informations. Like people can use this INSAR to measure the Earth surface and then to estimate the groundwater storage in space domain. And also people trying to measure the near surface gravity changes by these two satellites, which called GRACE mission, to derived to match, and the recent study shows that this near surface gravity changes are significantly affected by this groundwater storage. And then if for this central Oklahoma, from the government report, due to this inadequate water supply, the white production in Oklahoma and Kansas has been reduced by about 7 to 8% in 2021. That's make us to focusing in this central Oklahoma array and start this project. And another advantage of this study region is that it includes two major groundwater aquifers. One is Gabriel Willington (GW), and another is this Vermosa VA aquifers. Those two aquifers are actually the largest bedrock aquifers in Oklahoma that suppose that it's agricultural irrigations. And so therefore, we collect all those stations shown by these triangles in the figure and collect these vertical components, continuous seismic recordings from these 54 stations and within 9 years from 2013 to 2022. And but here, this figure shows the data availability of our data set. And what should be noticed is that because of this rotation and the maintenance of the station, we have some gaps from 2013 to 2018, which might affect our final results and our plan when we get to get there. So one slide to briefly introduce how we compute processable data and get the velocity variations. So the first step is to do the pre-processing. It's just following the standard routines established by the Benson in 2007. And so it involved this downsamplings. We downsample it to 0.05 seconds, and remove the instrument response and band pass filtering and detrain, demean. And the unique thing is we need to do the 1-bit normalization. So there's one parameter, is the frequency band is important. So we determine this into 0.1 to 1 hertz is because we use this 1D velocity profile to compute sensitivity depths of this fundamental relay, since there in current stage there is no good way to estimate the sensitivity depths of the coda-waves. So we use this fundamental relay waves as an approximation. So from those depth sensitivity curves, we can see from 0.1 to 1 hertz, most of energy are concentrated within 1 kilometers, which can perfectly coverage the depth distribution of the groundwater in central Oklahoma. Sorry, I forgot to put it, but the depths, the maximum depth of the groundwater in central Oklahoma is about 400 meters. So and after this pre-processing, we can compute the daily and assemble reference cross-correlation functions for each station pairs. So this figure shows the one example, like taking this one station pair as an example, and shows the daily cross-correlation functions for 4 continuous states. And because of the stacking, we can see this are almost similar. But when we compute the from time difference for the third steps, you can see the significant difference in this time shift. So this figure shows the all available reference cross-correlation functions from all station pairs. So I align it with this interstation distance, and you can see this move out this energy of this relay wave coming from the relay wave, and because our target is using this coda-wave, which is more concentrated with this small velocity perturbations. So we just cut it out and start just using the later windows to contain this strong coda-waves to do this computation. So once we get this daily and the reference, we can compute this using this certain doublet method, like a moving window spectral method, to compute the time difference between the reference and daily cross-correlation functions. And once we have all those travel time shift, and we assume that in this stage, we assume that the homogeneous velocity perturbations. So this travel time shift can be linearly transformed into the velocity variations, the temporal variations, and therefore we get these figures. So, and in these figures, we can observe two major features. One is this decrease, increase, and then decrease trend. Another is this seasonal cyclings per year, and those figures can also be distinguished in these two strong energies in these spectrums. And one thing we should mention is that we can see this from 2016, 2018, we have a large uncertainty or the large error variations, which we believe is because of the limited data availability during this time. Then since we would like to use these velocity variations to monitor the groundwater, so we need to build the relation between the seismic velocity and the groundwater storage. So we first compare our DVOV results, which shown by this blue line, with this gravity measurement, grace measurement. So we're happy to see that these two measurements shows a good anti-correlations, which suggests that there is the negative correlation between the groundwater and the seismic velocity. But this gravity measurement is still an indirect measurement, and we still want to find some direct evidence to support our hypothesis. Therefore, we are lucky enough to find there is a groundwater wells drawn by Oklahoma Geological Survey to continuously monitoring the groundwater depths of this GW aquifer, which shown by this blue line. And considering about the spatial variations of the seismic velocity, we use this 3 stations around these wells to recompute a local DVOV, which shown by this red line. So we can see, although this blue line, this local DVOV has large fluctuations in certain year, like 2019, but those two lines, those two results give a similar long-term trend. It's increase and decrease trend. So those two comparisons makes us believe that there is a negative correlations between the near-surface seismic velocity and the groundwater storage. But we do not want to stop at the groundwater. We want to check all the water resources near the Earth's surface. So we further compare the velocity variations and the droid. So here in this figure, from this colors from yellow to brown shows a different severity of the droid in central Oklahoma, and this black line are our DVOV results. So we can see whenever there is a droid event, there are always accompanying a local peak values in DVOV. Like in 2014, we have a very long time of droids, and we have this local peak values. And in early 2017, we have whenever we have a droid, we have this peak values. A similar thing with this 2018. And also even we have a very short duration of the droids, there is always company. There also have certain local peak values in DVOV, like in this droid event, we have these peak values, and for this droid event, we have these peak values. And then we also compare our results with the precipitations. So this blue line, our DVOV and downsample DVOV, and those blue line, red line are downsample DVOV, and the blue lines are the measured precipitations in central Oklahoma. So we can see whenever there is a larger amount of rainfalls, we have the local minimums in our seismic velocity. And where I see is inadequate of the rainfalls, we have these local peak values. So all those results shows us that this groundwater storage can help this long-term trend of the seismic velocity of the DVOV can be explained by this water storage near the Earth's surface. And then we are trying to use this air temperature to explain the seasonal variations of the DVOV. So here we use this thermoelastic equations to simulate this DVOV based on the DVOA by this temperature. So here are all the series of the model parameters which I borrowed from previous studies focusing in Oklahoma. Therefore, I can make these simulations more reasonable. So finally, we have this in this figure. This red line shows this air temperature, measured air temperature, and this green line shows this synthetic DVOV by this equation, and this blue line are the signal variations from our measurement. So we can see those when comparing with this peak and this blue line and the green lines. You can see these two are consistent with each other in both amplitude and phase. Although we have a certain phase difference from 2016 to 2018, yeah, and in current stage we plan this phase shift is because of the limited of data availability that generates large uncertainties. And then since when we plot the station for this DVO using the DVO in a 2D map, we can see this two is the recoverage of this of our observation are pretty good. So it makes us put forward to from this spatial variation to from temporal variation to spatial temporal variations. And in this case, we cannot assume we cannot assume the homogeneous velocity perturbations, but using this specific kernel of the coda-wave interferometry to add the spatial informations into account. So this equation connects the travel time shift and the velocity variations. And this equation can be easily written in the metric format. So we can finally use this least square solution to get our special variations of this DVOV. And because this figure is one example is the kernel of coda-wave interferometry for one station pairs, taken as an example. And then we finally get these figures. So in this figure, we extract 4 days of the velocity spatial velocity of the spatial variations of the seismic velocity, which is shown by this first row, and then we compare it with this INSA measurement shown by the second row, and this third row is actually the estimated groundwater changes, mainly computed by the GRIS measurement. So we are lucky to see that for most of the data, these 3 measurements show a similar spatial patterns. And if we like focusing in this 2020 January 31st, we can see for this JW aquifer, we have this velocity increase, which from our hypothesis, it should indicate velocity groundwater discharge. Yeah, groundwater discharge. And we're lucky to see this decrease of the surface elevation measured by INSA, and also the decrease in the groundwater, negative in the groundwater changes. So those spatial variations also support our hypothesis that there is a negative relation between the groundwater storage and the seismic velocity. So those are all the observations and comparisons in data in the different data. So we are trying to give the mechanisms to get 2 possible, well, simple but possible mechanisms to explain these negative correlations. So the first possible mechanism is from this pore pressures. So if we go back to this comparison between the DVOV and the GRIS measurement, and this GRIS measurement is actually the unit of it is meter, is represented by the water equivalent thickness. So it's centimeters, and we can easily and we use linear regression to connect these 2 measurements and get these equations. So from this linear regression, we can see most of data located within 2 sigmas. So which means this this result is pretty accurate, is somehow reliable, and then we can use this buoyancy law to transform this equivalent thickness into the pressure. And we finally get this stress sensitivity as to negative 1.72 times 10 to minus 7. And learning from the previous study, there's several people, and one representative result is they measure the Umamara. They do a real examinations in the field measurement and measure the stress sensitivity in one groundwater storage in Japan. And from this paper, from this results, their stress sensitivity in real world is about 10 to minus 7 per Pascal, which is consistent with our these rates, these values. So this help us think this pore pressure might be the one possible explanation for these negative correlations. And another thing is for the density. So we built this simple 2D models. And if you use this simple VRH approximation, this apparent velocity for this two-layer models can be expressed in this equation. And if you substitute this V1 and the first layer, second layer by this shear velocity and the elastic modulus, this velocity can be this apparent velocity can be rewritten in this equation. And if we assume that the total depth of this two-layer model is about 100 meters, and if say assuming a discharge occurs, recharge occurs, it means this L1 increase from L1 decrease from 6 to 5, and we do see the velocity increase in the shear water, the shear velocity by dVOV and the which result in the dVOV by 0.03%, which is the magnitude is consistent with our real measurement in Oklahoma. But those are the very simple, tiny, naive mechanisms. We need more investigations on to understanding these negative correlations. So finally, as a conclusion, we successfully built this 3D velocity model, which can enable us to better delineate geological province in Oklahoma, such as this Anaco Basin and Track platform. And this radio entropy might help us to understand the different geological deformations, like the sedimentary layers in shallow in uppermost crust, and also all these entropic minerals in the middle crust. The synthetic test shows that the significant impact of the seismic velocity for this earthquake location, especially for this focal depths. So this means this our inverted 3D velocity model give us an opportunity to reinvestigate this induced earthquake in Oklahoma. So we also compare based on the comparison among the dVOV and the gravity and the groundwater depths, we can see we conclude negative correlations between the groundwater and the near surface seismic velocity in Oklahoma, and the signal in current stage we only explain these signal cyclings based on these temporal variations, and through this thermoelastic effect. Therefore, our results on this dVOV shows the potential of the using seismometers to monitor the water storage, which is important for the sustainable water management and the estimation of the water deficit, and with a higher temporal and spatial resolutions. So that's all for my presentation, and some of papers relative to this presentation are shown here. So I'd like to get any comments and suggestions.
Yeah, you have any questions? Yes, ma'am.
Thanks for giving this talk. I first have a question about your data. I mean, you are windowing the data over 1 day periods. That's impressive. I was wondering if there's any seasonality to the quality of the source, and whether if you, for example, look at the spectrum of your travel time variations or velocity variations, whether day-to-day variations are very significant compared to seasonal variations.
Right. Well, it's like a common question on whether your signal variation is coming from the source or the material itself. And so for this, I didn't show in my presentation, but we do test the we do have certain tests. We assume that this source may come because of the ocean tide or the signal wind. So we compute group the station pairs based on the azimuthal angle, and compute the signal the DVO wave based on different azimuthal angle, and which the result shows the similar between different directions. And the second thing is I do not too worry about these signal variations, is because we use, as mentioned, we are not we don't want to use this first arrival, this periodic energies, but use this higher scattering coda-waves, which means that yes, as a first several scattering, it might be highly affected by the source. But if after so many scatterings, this source effect will be somehow mitigated.
Okay.
Thank you for a really good talk. I was just wondering, could you explain a little bit more about why your data gap in kind of like 2018 would lead to a phase shift? Yeah.
Oh, it's our current explanation is because of this large uncertainties. Although currently we have this mean and median value shown by this blue and black line, but since we have this homogeneous velocity perturbations and also this lack of the enough data to stake, so the real case could be it varies within these large variations, and then if you keep these variations into account and go back to this seasonal cyclings, we can see it if taking this account, this green line is actually within the arrow uncertainty region of this blue line.
Thank you.
Yes.
I was wondering, can you go back to the figure that shows the comparison of your velocity, your temporal velocity variations with the well water data? So the comparison between the well data and your velocity model. Yes, exactly that one. So on the lower figure, so I definitely agree that kind of the long period signal matches very well, like that's very convincing. But I found it a little surprising that you see variations in velocity that are kind of on shorter timescales than the water retrieval. Like I might not have necessarily predicted that.
So it means the red line is shorter than.
Yeah, like the red line has variations on shorter timescales. Kind of it's less sort of smooth than the blue line. So I'm just wondering if you think that do you think that those variations are real, and is there something that's affecting the velocity other than the groundwater removal? You know what I mean?
So yeah, I understand the question, but let's see. We do think of whether there is a certain real environmental effects that's resulting in this sudden change. But currently we cannot explain too much. Actually the similar answer is that we have a very limited of the station pairs. We only have 3 stations. But for when computing this this temporal variation of DVO, it needs many stackings to remove these uncertainties and also the singular values from certain spatial station pairs. So if I only have the 3 stations, it's hard to explain this short term.
Thanks.
Yes.
Thank you. Very nice talk. I have a couple of questions. First, in terms of the relocation, so it's straightforward to use earthquake location to verify the reliability of Earth's model. So my question is, how do you quantify the relocation or location results in terms of the reliability of your model? So it's I mean it's qualitative to verify which model is better in terms of how clustered the result is. But do you have any quantitative way to validate the accuracy of the velocity model?
Yeah, that's let's say one good question is that we don't have too much like numbers to quantify it. So our current like we assume that this our new result is better is based on the geological informations, like some geological profiles, some reports from the ODS. They have this they have this sorry. They have this like a false geometry, and for if if we go back to this SL catalog, which based on the one velocity model and plotting their spatial distributions, you can see a straight. Let me see the almost the dipping angle is almost 90 degree. It's almost vertical, but from this animation, we can see certain dipping, the rotation of like changes in the dipping angle, which is consistent with the geological profiles. Yeah, but yes, these are problems.
So it's still a qualitative evaluation. Okay, good, thank you. My second question is, what's the main advantage of the dV over V method compared with other mainstream remote sensing techniques?
Oh yeah, so like those
like GPS, GRIS, INSAR, to some extent, some technique like INSAR, it might have even higher spatial resolution. So what's the main advantage of using this seismological way to evaluate the same phenomenon?
Yeah, so like taking the INSAR for example, it can give us we cannot compete with the with the INSAR in terms of the spatial resolution. It can go down to centimeters. The seismic data may not have such kind of resolution, but this temporal sampling is determined by the satellite or the orbit of the satellite. It's commonly sampled per month, or well, recently it can go down to 3 weeks. So, but if you go to this droid evolution, you can see this. You can see this sudden, this is a very short duration of the droid, but very severe, but which may not be detected by the INSAR. So the purpose of we want to use this seismometer to monitor those like water storage is that it can balance the temporal and spatial resolutions. So it means we are not going to fight with this GPS and we are drawing in terms of the temporal resolution, but we definitely have the better spatial resolution than those two measurements, and we have better temporal resolutions than INSAR and GRIS.
Great, thank you. Yeah, my last question, just curious, what's your next step of this series of research?
So for this can
for both.
Turn to the two, since it's two products.
Yeah.
So it turn to two directions. One is for this waveform inversion. We do have during when we build this waveform inversion, we still use this local global based optimizations, and which bring us a lot of problems when we're solving it. That's why I come here to learn following professors to try if we can use this global optimization to help us mitigate this uncertainty issue. And for this and later, since as I mentioned, we have a collaboration with University of Toronto. They have a group to use the full waveform modeling to determine the source parameters, and we are trying to. And actually this is the original purpose of this project is we want to really understand the induced earthquakes in Oklahoma, because many of those studies are based on this statistic analysis. So we may try if say we can understand it from the physical models or not. And for this DVOV measurement, so currently is a start from the temporal variations and then go to the 2D domain with this simple, very analytical sensitive kernels. One work I'm interested in is to build a 3D velocity models and to include this depth information into account. So if you go back to this figure is in account, you can see for many, for these days, these three measurements have a good correlations in spatial patterns. But if you go to this February 25th, we have a good correlation between the DVOV and the INSAR, but this gravity measurement is somehow deviate from us. So far, our guess on this observation is that these three measurements is coming from the different mechanisms, and this groundwater, this grease measurement might be deeper than INSAR and the DVOV. So if we can have a certain 3D kernels and to taking this depth information into account, we may help to mitigate this disagreement.
Great. Are you last question? Are you interested in Texas seismicity and the structure? Because we are Texans, so you can you are free to collaborate.
Thank you. Yeah, most likely, hydraulic fracture induced. Yeah, but I cannot say 100%.
Great talk, and I was wondering, I mean, for the DVOV, you use the 1-bit normalization, so you don't have the amplitude information. And in the future, is that possible to include the amplitude information in the cross correlation and to better constrain some elastic property?
Yeah, it's a good question. I know someone using this amplitude inside out phase information, but amplitude to measure this groundwater changes. From their report, they have somehow better results in some areas, but I'm still doubting it because of the amplitude affected by even more factors than the phase information. So it's somehow difficult to explain where this amplitude comes from.
Sure. There are no more questions. And one thing I was really appreciative of that you've actually tried to build a rock physics model to explain the dV by dV, which was missing earlier. Even though better models can be built, but this is a good start.